So welcome to the next session. The next session is the NextG or the 6G session, where we are going to be talking about the next generation of wireless systems. With 6G, people are talking about more speeds, lower latency, and there are some key enablers such as smart surfaces, joint communications plus sensing, more bandwidth, new payment systems, and we'll cover some of the latest advances in today's wireless and NextG session. Our first speaker is Kun Wu Chu, goes by Casey. She's a PhD candidate advised by Professor Kyle Jamieson at Princeton University. Her research focuses on developing software, hardware, reconfigurable intelligent surface systems that scale up efficiency of 5G networks. Today, she will present work on reconfigurable intelligent surfaces for LEO satellite networks that face coverage problems in urban areas.
Thank you for the introduction. Hi, my name is Casey, and today I'll be presenting my work on dual band reconfigurable metasurfaces for satellite networking. So recently, there has been much interest in low Earth orbit satellite networks, with multiple companies like Starlink, OneWeb, and Telesat in their various deployment stages. It has advantage in terms of low latency and large coverage from faster multi-hops. And there are various use cases for LEO satellite communication. So for example, there is advantages in transportation system, and also for the coverage in urban canyon and rural areas. But there are challenges for each application as well. So for example, for transportation, it requires a complex beam alignment and beam tracking and handover procedure because both satellite and user are moving rapidly. Also, the tall buildings in the city often blocks the line of sight and precludes the area of coverage, such as a street. Another challenge is that most of the time, the current system requires a bulky, expensive, high-gain antenna dish and use gateway to forward traffic from satellite to the user, which is power consuming. So while the current implementation sees the limited uses, we believe that RIS, a reconfigurable intelligent surfaces, can enhance their applicability and improve the performances. So for each application, I believe the RIS has an advantage. So for transportation system, we can mount the RIS on the window so that it can enable a fast beam alignment and soft handover by beam splitting and beam combining to multiple satellites. Second, RIS can support both beam refraction into the building for the users inside and also reflect off of the building to provide services in the street level. Lastly, it can replace the role of the bulky power-consuming antenna and also get rid of the gateway, so it consumes much lower power. For example, it consumes about hundreds of microwatts order of power. Particularly for the first application, it can enhance satellite-to-satellite handover by combining beam, downlink beam into the user from multiple satellites. On the other hand, for uplink, we can divide the energy into two different satellites. So once the primary link is moving away, we can, before it gets disconnected, we can search for the secondary satellite and then establish a link so that the link is not interrupted when the primary satellite goes away. So in our previous work, we have proposed and then prototyped and demonstrated the feasibility of Huygens surface for being able to relay the beam in forward direction for transmissive relay and backward direction for the reflective relay. Also, we show the capability for Huygens surface to split the beam into multiple directions and combine the beams. And if we look at the surface in the close-up, we have an array of unit cells, and we have two different unit cells facing opposite to each other. So first one is called magnetic meta-atom, responsible for magnetic field. And second unit cell is called electric meta-atom, responsible for electric field. And for each unit cell, we load a component called varactor, and which if we apply a different voltage value to the varactor, we can basically change the phase of the incident wave. And this is very useful, but the problem of this is that it only resonated at one frequency, which was millimeter wave for our previous work. But in Leo's system, it uses FDD, where downlink frequency and uplink frequency differ by at least 4 to 5 gigahertz. So now our challenge becomes, how do we design a surface that works for both lower Ku band and upper Ku band? So there are naive ways that we can think of. One way would be having two single band RISs, one for downlink and one for uplink. But this is problematic because it requires a separate beam training, which doubles the overall delay. Second way could be partitioning the surface into two subsets with each resonating at a different frequency. But this basically reduces the number of useful element given the surface area, and which reduces the directivity gain. So now our new challenge is, how do we design a bi-resonant surface element? So we went through several designing stages, and I'm gonna step one by one. But before that, we want to show how the single band resonator look like. Here you can see that on left, there are single band resonators that resonate at one frequency, which is a frequency of the downlink. And we want to note that actually the resonant frequency is inversely proportional to the size of the resonator. So if we scale the size down, it will resonate at a higher frequency. So one would think that we can just miniaturize the size of it and overlap it on top of the one on the left. And at the end, we can actually get a dual band in this case, but this is also problematic because you're basically having two separate control over uplink and downlink. And this means that we have to load more varactor for the control, which not only increases the implementation costs, it adds the insertion loss, lowering the efficiency, and also it complicates the biasing control. So we really want to simultaneously control the uplink and downlink. So how do we make this inner ring and outer ring share a one control, which is a varactor? So one way we were thinking was maybe how about just overlapping, letting them share one varactor. But what we observed was that if we do this, only the outer ring resonates and the signal does not pass into the inner ring. So again, this becomes a monoresonant unit cells. So to make it bi-resonant, what we do is we load something called a RF choke between the bridging part of inner ring and outer ring. So RF choke is basically blocking the signal at a high frequency and letting the signal at low frequency to pass. So this way we can kind of isolate the current oscillation of the inner ring and outer ring. And one way to introduce the RF choke is provide a high impedance using a commodity inductor. So here our method was just installing the inductor on the bridge part. But another way to introduce RF choke is have a thin and long copper line. So the thinner and longer it gets, the higher impedance it provides. So it kind of mimics the inductor. So this way we were also able to isolate the inner ring and outer ring. But the problem is that for electric side, the spacing between inner ring and outer ring is so tight. So if we are trying to load the copper line in between, we need to either scale the inner ring smaller or outer ring larger. And this makes the frequency difference of downlink and uplink too far apart. So at the end, what we use is a combination of both approaches. So for electric side, we use inductor-based isolation. And for magnetic side, we use meander-based isolation. And this is some simulation result where for the 10 gigahertz downlink, you can see that outer ring is resonating and creating a field. And for the 15 gigahertz uplink, the inner ring is resonating and creating the field. So at the end, when we vary the voltage applied to electric side and magnetic side, we get something called Huygens pattern. So on the top row, it's showing the magnitude of the relayed beam, and the bottom is the phase of the relayed beam. So for transmission side, when we, so here, UM is basically voltage applied to the magnetic unit cell, and UE is voltage applied to the electric unit cell. So if we look at the area where the arrow is pointing at, we are getting a very high efficiency. And also at the same time, by changing the voltage, we can have arbitral phase distribution from 0 to 360 degrees. So this means that we can basically, if we have a particular steering angle we want, we can choose the area and we can choose the area points here and then apply that voltage and achieve the steering we want. And same for reflection. Now, instead of using the diagonal area, we are using a left bottom area where the efficiency is high and then phase coverage is dynamic. And one thing that we have demonstrated in our previous work was that the Huygens surface is actually angularly reciprocal. What that means is that once there is a downlink and you align the downlink signal to the user, without changing the configuration of the surface, you can, the surface is automatically steering the uplink signal to the direction of transmitter of downlink. So this way we can simultaneously steer a downlink and uplink to where the user and then satellite is. So in conclusion, our work is our first work that kind of proposes a dual band and steerable for both reflective and transmissive scenario, and also able to split and combine the beam, and is angularly reciprocal. And our future work, we're trying to focus more on how do we aggregate multiple satellite links, because bandwidth of a single satellite link can not really achieve the bandwidth of the fiber. So one way to outperform the fiber is basically aggregating all the link from the nearby satellites. So next step is how do we create an algorithm that provides optimal coordination of all satellites and surface and the user. And also we want to leverage defined satellite trajectories, although it might not be very accurate. We want to incorporate this into our searching protocol, beam aligning protocol. So this is the end of my talk. And if there's any question, I think I'm happy to answer. Thank you.
I'm Mohammed from UCLA, and thanks for the nice presentation. Very nice job. So this problem of dual band has been in the community for phase arrays too. And the phase arrays, the problem is that because the frequency ratio is 1.5 difference, right? Mm-hmm. The frequency difference is so high. So when you place your elements, for example, for some equal distances, you need different phase shifts for different frequency bands. How do you solve this in your design?
So at the end, we kind of run optimization because there are defined phase distribution that you kind of need for uplink and downlink for different frequency gaps. So we kind of did like an optimization for like an inner cell design, because you can kind of redesign the inner cell to make it like the phase to be relative to the outer ring. So that's one approach that we have done, kind of, yeah, like optimization with the software itself. Yeah.
Thank you.
So Casey, I have another question. So, one way to solve this problem people have talked about is use the Starlink kind of dish on top of your house and then have a Wi-Fi inside the house, right? That's the way people typically use satellite networks. We're talking about it has other benefits. Could you just elaborate some benefits compared to that alternative design of just using the dish antenna, the satellite antenna along with the Wi-Fi router?
So I think I have briefly mentioned regarding the power consumption and also the use of gateway. So generally the antenna at the receiving side for satellites, the Starlink, for example, is very high gain. It has to be very high gain, but based on our calculation, surface of 75 centimeters square can actually perform better than the antennas. So it has that advantage. And also at the same time, instead of serving only the users inside the indoor, you can also serve the user outside. So instead of homeowner owning the antenna, you can kind of install in the city infrastructure so that the service provider has a ownership over the surfaces, and then provide kind of like 5G services to across many users, whether this person is inside the building or outside the building.
Thanks, Casey. Just one last question. Are there any limitations to frequency? That is, can it be used in any part of the frequency spectrum, or is it mostly in the KU K-band, although you talked about 10 and 15 gigs as well?
So for our work, we have majorly focused on crew bands. And our previous work was also in like 24 to 28 gigahertz. But because of there's some limitation with the varioactor, I'm not sure about scaling above 70 gigahertz, but there could be more method using different component, not varioactor, but pin diode, for example, so we can change the component, but I think the logistic would still apply the same.
Thank you. Thanks, Casey. So let's thank Casey again. Our next speaker is Haofan Lu. He's a second-year CS PhD student at UCLA. He's working with Professor Omid Abari, whose lab works on different next-generation wireless technologies. Haofan's research is mainly in the area of wireless sensing and communication systems. He's also exploring the broad area of IoT. Today, he will talk about a very interesting piece of work to enable localization on any Wi-Fi device, even the ones that have a single RF chain.
So hello, everyone. I'm Haofan Lu from UCLA. Today, I'm going to talk about how to bring Wi-Fi localization to any Wi-Fi devices. This is a joint work with my collaborators, Tianxiang, Reza, Ali, and Omid. So Wi-Fi localization is the idea of using ubiquitous Wi-Fi signals to localize the other devices. It promises a lot of exciting applications, including home automation, smart industrial and warehouse, and smart food delivery. But most of these applications are not there yet. And the reason is like today's Wi-Fi localization technologies still have limitations. And to understand that, let me show you today's approach for localization. So one of the common approach for Wi-Fi localization is the multiple access point triangulation or trilateration. The idea is that they have multiple access points in the space. And each of the access points measure the distance or direction towards the target device. And a central computer will collect and analyze this information to find the location of the target device. And you can see the limitation of this approach is that it requires coordinations among multiple access points, which is not the case in most of the home, because most of us only have one access point in the home. And to solve this problem, later people proposed to use a single access point and trilateration to solve this problem. So the idea is that we have a single access point, yes, but we have multiple antennas on this access point. So each antenna can find the direction, distance, towards the target device. And the optimization algorithm is typically used to find the most likely spot that satisfies all these distance constraints. But now they solve the multiple access point problem, but they still requires multiple transceiver chains. So unfortunately, not all Wi-Fi devices today have multiple transceiver chains. And for example, most of the IoT devices today only have a single transceiver chain. And therefore, they cannot use any of these techniques for localization. Therefore, in this work, we ask this question: can we enable localization with a single transceiver chain? To answer this question, we proposed WiSight, which is a system that brings Wi-Fi localization to any Wi-Fi devices. And it works as a plug-and-play module without any modification on the Wi-Fi chipset. It also doesn't require any cooperation from the other devices. So to understand how WiSight works, let's start from the first principle of the localization task. Basically, if you want to find the location of the target device, you need two pieces of information, right? First of all, distance, and second, direction. People have tried to use a single transceiver chain to find the distance. The idea is basically using the data act to measure the round trip time. So in this talk, for the sake of time, I'm going to mainly focus on the direction finding using a single transceiver chain. So let's To understand why finding the direction with a single transceiver chain is a challenging problem, let's see how people today find the direction. The traditional approach for finding the direction is using an antenna array. The idea is that we have multiple antennas, and each antenna measures the phase shift of the received signal. And we look at the phase shift across the antenna array. We can understand where does the signal comes from. But as you can see, the problem is that it requires multiple transceiver chains, and each one should measure the phase shift. And again, so we ask this question, can we measure direction with a single transceiver chain? Because if we can do that, we are essentially bring localization to any Wi-Fi devices. So our solution to this problem is to use the frequency scanning antenna, or FSA. What's an FSA? FSA is a passive antenna structure. It consumes no power. It receives signals of a certain frequency in each direction. Let me show you an animation to illustrate what I mean. So let's see, this is an antenna. And if we have a signal of frequency F1, it can only be received in this particular direction. And if we have another signal of frequency F2, it can only be received in this direction. The same thing happens to F3, F4, and other frequencies. So the takeaway message here is that there's a one-to-one mapping relationship between frequency and direction. And this is our key to finding direction using a single transceiver chain. So now that we understand the working principle of FSA, now let's see how we can use FSA for finding the direction. So I'll show you this example. Let's say we have a Wi-Fi device with a single transceiver chain, and we want to localize a target device, which is transmitting some sort of signals. What we should do, we first replace the original antenna with FSA. And now you can see different frequencies corresponding to different things. And during the process, we will plot this graph, the received signal power of the Wi-Fi devices, and with the frequency channels. Let's say the target device first transmits on frequency F1, and we receive this amount of power because the bin is not aligned. Now, if the target switch to frequency F2 and transmit the signal, we receive more power because now the bin is aligned. The same thing happens to frequency F3, F4, and F5, and we plot it out. Now you can see that frequency F2 has the most strongest power. And remember, there's a one-to-one mapping relationship between the frequency and direction. And therefore, we can say that the target device is at the direction pointed by frequency channel F2. So, but if you are familiar with Wi-Fi protocol, you may ask this question. Wait a minute, Wi-Fi device typically only work on a single channel. How can you let it to switch to different frequency channels? Right? Remember, we don't want any cooperations in our system. So our solution is to use the probing mechanism of Wi-Fi. Basically, probing is an inherent process of Wi-Fi protocol to finding new surrounding access points. Your phone is constantly probing on different frequency channels to find the potential access point you can connect it to. So Wi-Fi probe requests, it's basically the probing just sending some probe request packets, and it's broadcast on every frequency channel, and it's unencrypted, so every device can hear it. And we found that it's actually independent of whether your device is connected to a network. Even if your device is already connected to a network, it's still probing to find other potential networks to join. So to conclude, our approach to find direction is using FSA together with the probing mechanism. In this way, we can basically find the direction using a single transceiver chain. Now, let me show you our evaluation setup. This is our prototype frequency scanning antenna. And we designed two prototypes, one with 8 antenna elements, one with 4 antenna elements, and have different size. And in the evaluation setup, we connect one of these antenna to a Wi-Fi device, and we try to find the target device in this case. So let me first show you our simulation result of the FSA. So let's say if we have a signal of frequency 5.49, and if I remember correctly, it's the Wi-Fi channel 100. And you can see the beam, we have a strong antenna gain at the angle of around 30 degrees. And if we sweep the frequency up to 5.57, I believe it's channel number 116. Now the direction points to around 15 degrees. And as we sweep up the frequencies, you can see our beam sweeps. And there, as you can see, there is a one-to-one mapping relationship between the frequency channel and direction. And therefore, we can use this property to find direction using the method we mentioned before. Now, let me show you our preliminary result on direction finding. So in this plot, the x-axis is the target device direction, basically the ground truth. The y-axis is the estimated direction. And this red line indicates the target, our estimation matches with the ground truth. And you can see now these blue dots are our measurement result, and it matches pretty well. And although we didn't mention our distance measurement technique, let me show you our distance measurement result too. So the x-axis again is the actual distance, the y-axis is the estimation. And this red dot line is again the matching between ground truth and the estimation. So our distance measurement achieves around like sub-meter level median error, and which it's pretty good for like low-cost IoT systems. So to conclude, in this talk, we propose WiSight, which is a system that brings Wi-Fi localization to any Wi-Fi devices, even with a single transceiver chain. We believe we just scratched the surface, and there's a lot of exciting applications you can enable with this technology. To name a few, for example, Wi-Fi for wireless sensor networks, each sensor node can find the direction of other sensor nodes. And maybe there's some exciting interactions between them we can use this technology to enable. And there's a few future research direction, like how can we deal with the multipass effect, and how can we improve the FSC scanning range with limited bandwidth, and how can we integrate to other applications. Okay, that concludes my talk. Thank you so much for your attention.
Thank you for the interesting presentation. I have one question. Will this system affect the communication function of the normal AP?
Yeah. Thank you for the question. So we are still investigating that. There's a few ways to look at about this. So why this system may affect the normal traffic of communication? It's like the direction of that antenna points to different direction, not necessarily. The common Wi-Fi use omnidirectional antenna, so every device in the space can hear it. But now maybe the direction being points to a different direction towards rather than the target device. So can we still hear that? Maybe we are going to evaluate that in our follow-up work. Yeah.
Thank you. Thank you for your explanation.
Thank you.
Thanks a lot. Very nice idea. I was wondering, how does it work for moving targets given the probe rate of,
Yeah.
I mean, would it work when targets move?
Yeah, thank you for the good question. And for mobility, of course, it's a big issue. And as you know, like the probing rate is around 10 seconds. And so it may not work. So, but we are thinking, can we do other things? For example, Wi-Fi use OFDM, And it divides the basic idea is it divides the frequency, a whole channel into different subcarriers. And our idea can also apply to that, basically using different subcarriers instead of different channels to find the direction. That's what we are going to explore in our follow-up work.
But that would also need probing, right?
No, in that case, we only need one packet to find direction. We don't need to scan for different different channels.
So you would have a better resolution.
Maybe, yes.
Thanks.
Thank you, Hoffman.
Thank you so much.
Our next speaker is Dong Lee. Dong is a fifth-year PhD student from UMass Amherst. He's advised by Professor Jay Xiong. His research focuses on enabling novel acoustic sensing applications on commercial devices, including localization and tracking, human-computer interaction, and health sensing. He will be on the job market next year, and he's starting from the end of the year, and he's open to industrial lab and faculty positions. Today, he will present a new technology to accurately track displacements using sound signals.
Thank you for the introduction, Ranvi. Hello, everyone. My name is Dong Li. I am a fifth-year PhD student from UMass Amherst, advised by Professor Jie Xiong. It's my great pleasure to present our recent work, boosting the sensing granularity of acoustic signals by exploiting hardware nonlinearity. This is a joint work between the Duke University and UMass Amherst. In recent years, wireless signals have been widely employed for sensing, including Wi-Fi, RFID, and LoRa. Compared with these signals, acoustic signal has its own unique advantages. For example, fine sensing granularity and wide device availability. In case that some of you may not be familiar with acoustic sensing, let me briefly introduce its basic idea. The speaker sends out inaudible acoustic signals in the air, and the signals are reflected by a target and then received at the microphone. By analyzing the variations of the received signals, we can sense the context of the human targets. For example, hand gestures, respiration, and eye blink. Speakers and microphones are essential components for almost all devices around us, including smartphones, smart speakers, smartwatches, earphones, etc. With this unique advantage, acoustic sensing shows great potential to transform billions of devices into ubiquitous sensing platforms. Recent years have witnessed a widespread interest of acoustic sensing in the research community. They devoted their efforts to pushing the boundaries of acoustic sensing, including improving the sensing resolution, enabling new applications, and extending the sensing range. In this paper, for the first time, we demonstrate the possibility of boosting the sensing granularity by exploiting the nonlinearity on commodity devices such as smartphones. To detect the subtle movement, for example, machine vibration, the received signal is first converted into the IQ trajectory on the complex plane as shown in the right figure. The received signal contains the static path vector and the dynamic path vector. As shown in the left figure, the static path vector is the resultant of the direct path from the speaker to microphone and the reflections from the static objects, for example, a wall. While the dynamic vector is a reflection from the moving target, for example, a vibrating machine. For subtle movement such as vibration, the dynamic path vector rotates with respect to the static path vector. The extracted phase variations can be used to detect the subtle movement. To extract the phase variation, we first estimate the arc center of the IQ trajectory and then compute the phase with respect to the arc center. However, when the scale of the target movement reduces, the length of the IQ trajectory also decreases. And a short IQ trajectory can lead to inaccurate estimation of the arc center, and thus inaccurate phase extraction. This is a well-known challenge for prior studies. To address this challenge, we exploit the nonlinearity of commodity devices to boost the sensing granularity. The nonlinearity generally exists in the components of microphones, such as amplifier and diaphragm. Specifically, if the received signal reflected from the target is S in, the output signal S out after passing through the microphone can be represented as the sum of multiple nonlinear terms. And the nonlinear terms will introduce extra frequency components. We adopt chirp signal for fine-grained movement detection. As shown in the figure, chirp signal is a frequency modulated sine wave whose frequency sweeps linearly over time. And the received signal is a delayed version of the transmitted signal. We multiply the transmit signal with the received signal to derive the intermediate frequency signal, and the phase is extracted from the intermediate frequency signal. The received signal contains the direct path signal from the speaker to the microphone and the reflected signal from the moving target. The nonlinearity of microphone introduces extra intermodulated signal, which is caused by the intermodulation between the direct path signal and the reflected path signal. Through the mathematical proof, we verify that the phase variations for the intermodulated signal are multiple times larger than those of the original signal. Please refer to our paper for more mathematical details. We implement our proposed system on the ReSpeak platform and 5 different brands of the smartphones. To mimic the subtle movement, we place the target on a linear slide, has a movement precision of 50 micrometer. As mentioned before, the larger the phase variations, the better the sensing performance. This figure displays the extracted IQ trajectories for both the original signal and the intermodulated signal. We can observe that the IQ trajectories rotates more for the intermodulated signal than the original signal, which verifies our previous theoretical analysis. Furthermore, we find that besides the third order intermodulated signal, there also exists higher order intermodulated signals. And as the order of intermodulation increases, the phase variation also increases, which can be exploited to achieve better sensing performance. We conduct experiments to compare the performance of the original signal and the intermodulated signal when the target vibrates at different amplitudes. We can observe that the intermodulated signal outperforms the original signal when the vibration amplitude decreases, indicating the effectiveness of boosting the sensing granularity using the nonlinearity. We also evaluate different impacting factors for our proposed system, including different distances between the target and the sensing device and the various target reflection materials. With all this, I would like to summarize this paper. While microphone nonlinearity has been adopted to enable new applications in security and communication domains, we propose to exploit the nonlinearity of microphones to boost the sensing granularity for the first time. And we mathematically show the feasibility and also conduct benchmark experiments to demonstrate the effectiveness of the proposed idea. We believe this work can push the granularity boundary of acoustic sensing and benefit a large range of real-life applications. Please allow me to advertise myself once again. I am on the job market this year, and I am interested in industry labs and factory positions. If you have any openings, please let me know. That's all for my presentation today. Thank you for your time. I am ready to take any questions.
Thank you, Dom.
Hi, thanks for the great talk. I'm Anup from CMU.
Mhm.
I was trying to understand, so is it just that you can identify the amplitude of the vibration, but also like, can you identify the direction and also like the velocity of the vibrations? So if I have small finger movements, like, can you track and like use that to like build HCI systems like where, oh, my finger movement will like tell how much to scroll the screen or things like that? Or is it just, it's a vibrating machine and you can just tell the amplitude? Like,
Thank you for your question. Actually, it's a good one. So the reason why we use the vibration system to verify this idea is that for finger movements, it's usually in the scale of centimeter or millimeter level, right? But for our vibrating system, it's in the scale of sub-millimeter level or even sub-millimeter level. So to your question, our system can completely be applied to check your finger movements, and that is already like well studied in the literature. So the point in this paper is that we can achieve even more fine-grained movement checking in the scale of like a sub-millimeter level or sub-millimeter level. Yeah.
I guess just to rephrase, like, is it just that you can track the vibration amplitude, but can you also like, okay, I understand that finger tracking might be at a larger scales, but even at smaller scales, is it just that you can infer the amplitude, or can you actually infer, or does the speed of the vibration matter, or does if it's just one iteration that the machine just moved from point A to point B, can you track that, or does it have to be continuously vibrating?
It doesn't have to be vibrating. Yeah, we can check even if you are moving in one direction or any like random movements. Yeah.
Okay, thank you.
Thank you.
Thank you for the exciting research. I'm looking at the research from another aspect. So I'm looking at FMCW signal processing.
Yeah.
And in FMCW, you say that the range resolution is limited to the bandwidth that you're using.
Yes.
So according to the bandwidth you're using, I think 2 kilohertz of acoustic bandwidth, it gives you around 80 centimeter. But now you have developed another technique based on nonlinearity. What is your limitation? What is the resolution based on equations?
Mm-hmm.
How can you define the limit of this approach?
That is a good question. So the bandwidth we use for this paper is like 2 kilohertz, but as you mentioned, the resolution according to the relationship between the bandwidth and the resolution is like 8 centimeter. Yeah, that's correct. The resolution is for like resolving multiple targets, right? Here we are only targeting the movement of one target. So the working range for our system is like 20 centimeter. So we assume that within this short range, we will only have one like reflection from the target. And the sensing granularity, actually it is proportional to the frequency of our transmitting signal. So for example, for our work, if we use like 20 kilohertz transmitting signal, if the phase rotates for one circle, 2 pi, the distance change will be like 8 millimeter. Yeah, this is two different. These are two different stories: resolution and the granularity.
So one other approach can be just increasing the frequency of the carrier, right?
Yeah. That is a straightforward method, right? If we can increase the sample rate or the frequency of the signal to like 100 kilohertz, then everything works. But the key problem is that in commodity devices, the sampling rate is usually limited to like 48 kilohertz, right? That's why like we are trying to break the limitation of the sampling rate to increase boost the sensing granularity.
That's nice. And last question.
Mm-hmm.
So you are creating intermodulation and you're creating a harmonic. So you should be careful that there is not an object in the bit frequency of the higher frequency. And
that is a good question. Yeah, that's true. We must confirm that there is no object in the modulation frequency. Yeah, that's true. That's true.
Thank you so much.
Thank you.
Thank you for a great talk. It's very interesting research. So my concern about like you propose to use higher order nonlinearity for better granularity, if I understand correctly.
Yeah.
So, but in my experience, those high order, third level, third or seven, even seven, nonlinearity harmonics are very weak, and they can be buried by the noise floor. And how do you like think of this question, and do you have any solution?
Yeah, thank you. That is a good question. So we evaluate this impact in our paper. We found that different devices have different degrees of nonlinearity. So basically, like for some devices, we observe this phenomenon can be much severe, which can be exploited to boost the sensing granularity. But for some devices, it's true, it's very weak. That, yeah, that is one problem. And another thing is that different from like directly using the third order, signal, we are using the intermodulation between the direct pass and the reflection pass. So the strength of the direct pass is very strong because the relatively small distance between the speaker and the microphone, right? This helps us like boost the intermodulation signal we find here. Yeah.
Thank you so much.
Thank you.
Thank you, Dong. Let's thank Dong again. And our last talk is on blockchain and wireless systems. So this talk is given by Sarhat. He's a fifth-year PhD student from Stanford. He works with Nick McEwen and Sachin Katti. He mainly studies how to extract the most effective telemetry from different types of networks to make them more controllable. In the past, he worked on extremely precise congestion control for high-speed data centers. Nowadays, he's working on bringing controllability to cellular networks with a systems approach. He will be in the job market next year as well. Today, he will present an interesting approach on decentralizing cellular networks.
Okay, cool. All right. Hello, everyone. My name is Sarhat. Today, I'm going to be shifting the gears a little bit and talk a little bit about how we can use the technologies that were described a couple of minutes ago and build systems on top of it. And in specific, I will be talking about our vision for trust-free service measurement and payments for decentralized cellular networks. All right, so let's start with the challenges with today's centralized cellular operators. So first of all, buying license to start providing cellular service in an area is extremely expensive, right? For example, the 5G auctions costed $81 billion to the operators in the US, which is obviously not that feasible for new players in the game. And even if you can afford to pay that much, it is still difficult to cover the entire country. And this is mainly because of how propagation characteristics of 5G signals make it less profitable to provide service in some areas. And as the frequency spectrum of the new generation technologies increase, their range decreases. And as a result, this means operators need to deploy much larger number of radio units with this new generation. The millimeter waves cannot even propagate into the buildings. So there's this challenge coming. And according to Statista, people in the US with a 5G capable handsets spend only 25% of their time connected to a 5G network in the second quarter of 2022 in US. So clearly there is no single network that works everywhere, and operators are having some difficulty in providing widely available service. Okay. Therefore, instead of this, we propose decentralizing the cellular networks. This is much like how internet works today. In such a decentralized environment, we would allow anyone to start providing cellular service without any expensive licenses or countrywide networks. And then users would be able to connect to any available provider to start service of their choice. And we envision that this would enable on-demand slicing, where users would be able to dynamically negotiate for the details of their service. All right, so how does this really work? So today, when a user wants to connect to a provider, they need a trusted authority. This trusted authority can be a virtual operator like Google Fi, or the home operator if the user is roaming abroad, or the broker that was described in the Selbrecht's paper. The user first subscribes to this trusted authority, which then talks to the service provider to authenticate the user and bill the user with the transactions. And only then the connection between the provider and the user can be established. Note that here the user does not have the power of mandating what kind of quality of service they want to receive. Only the trusted authority has the power to talk to the provider about this, but the trusted authority does not have the visibility into the instantaneous needs of the user. Therefore, today, generally, this service here is best effort. However, the user knows exactly what kind of service they want, and the provider knows what is feasible for them to provide. Then we ask, why don't they just directly talk to each other and negotiate for the service dynamically? And for this purpose, we describe two-sided measurements where both entities independently monitor the service they provide and receive. And the user pays for this service only when it is satisfied with its measurements. And obviously, this payment needs to be recorded at some other place so that we make sure users don't end up spending money they don't have. A public immutable database that keeps the financial records of all the entities is good enough for this purpose. And ideally, it would also be trust-free to prevent any bias towards the financial records. And therefore, we propose using a blockchain bridge instead of a trusted authority in this setup. So, okay, how can we incorporate blockchain into this cellular environment, right? We introduce mini telcos, which are basically the service operators with an arbitrary number of base stations, even just one. In addition, they would have the measurement services for their side of two-sided measurements and a bridge client that talks to the bridge for the payment transactions. Well, the bridge is an independently owned entity that mediates those transactions between the users, mini telcos, and the blockchain itself. The session manager handles communication with the users and mini telcos, and the blockchain interface talks to the full blockchain node. In addition, the micropayment manager keeps track of payments coming from the users and forwards them to the mini telcos. When a mini telco wants to start providing service in an area, it establishes sessions with some subset of the bridges in the area. And with that session, the mini telco declares what kind of services are available, what are the slices, and what are the prices associated with those. With that information, they go ahead and sign a supplier contract on the full blockchain node. Note that finalizing this contract on a full blockchain node may take minutes, depending on the blockchain technology. Therefore, it needs to be finalized before the mini telco actually starts providing cellular service in the area. Similarly, when a user wants to receive some cellular service in that area, it again establishes sessions with some subset of the bridges, and they go ahead and sign this consumer contract on the full blockchain node. This consumer contract declares the escrow amount for the future payments of the user. Then, when a user wants to talk to a mini telco, wants to connect to a mini telco, it will ask the bridge about the available services in that mini telco, and the bridge will respond with the price information for that service. If the user agrees on the price and the service details, it'll start sending incremental payments, we call them micropayments, to the bridge, as long as it remains satisfied with the service it is receiving. And the bridge will forward that payment to the mini telco after deducting some commission. So the commission here incentivizes the bridge to correctly forward incoming payments, because otherwise mini telco would not receive the expected payments, stop providing service, and the user would stop paying. The bridge would end up collecting less commissions. Of course, one of the biggest technical challenge in the cellular environment is to determine how to reconcile two-sided measurements for this service verification. Namely, the timing and location of the two-sided measurement within the networking stack plays an important role in the robustness of the system. So in order to investigate those challenges, we are building a mini telco prototype and to run some over-the-air experiments. And we run hyperf traffic from between our user and some server in the internet while the user is connected to our mini telco with varying channel conditions. Then we measure the usage and throughput at the user, but also at two different locations at the mini telco. The first one of those locations is the P gateway at the core network of the mini telco. And the second location is the base station that the user is connected to. So the graph here shows how well those measurements match throughout the time with respect to different locations of measurements. Both the core and the base station measurements seem to match the user measurements really well, which is great news because this means mini telco can correctly adjust its payment expectations. However, you can see that the core measurements are noisier here due to the granularity at which we can collect measurements. And things actually get more interesting in the case of UDP traffic. So in this scenario, some packets start getting dropped in the second half of the experiment as the channel conditions get worse. And most of those packets get dropped in the radio network of the mini telco. Therefore, they cannot be detected by the measurement agent at the core. And the measurement agent at the core believes that all the packets that went through the P gateway of the mini telco were delivered to the user. And this creates a mismatch because the user did not receive those packets, so it will not pay for them. However, the base station is the closest point to the user. Therefore, it can monitor the actual service that was delivered to the receiver, the user here. Luckily, there's already some community effort that is working towards extracting some telemetry from base stations that we can utilize for those two-sided measurements. And we conjecture that two-sided measurements is reliant on extracting telemetry from base stations for the robustness of the system. So of course, we're not done with these preliminary findings. There are multiple other aspects of two-sided measurements and decentralization in general that we invite our community to start discussing for the future directions of research. And these would include, but are not limited to, what other kinds of two-sided measurements we can come up with and what would their overhead be, especially for the power limited user equipment we have. And how do you manage mobility and preserve privacy in this decentralized environment? For our initial responses to these challenges, please take a look at our paper. And with that, thank you very much. I'm happy to take questions, along with my blockchain expert colleague Ranvir here.
So hi, this is Wei Tao. So this is a very interesting work. I have one very general question. So if the payment or measurement is only based on throughput, does that encourage the customer to send their data very bursty way so that we can total services, the services level maybe downgrade?
Well, yes, that's a good question because that actually depends on what kind of service the receiver is interested in receiving or sending out. Depending on the application, yes, burstier traffic might be easier, and they might ask for like throughput for shorter periods of time, and then they would ask for best effort service for the rest of the time, which could be cheaper for them depending on the pricing. But if their application is not working well with burstier traffic, they will just try to find some other service that can provide the quality of service.
So you say they can decide how they can charge those traffic.
Exactly. So basically, this negotiation period between the user and the provider is when they talk about like, oh, I need this kind of service level agreements. This throughput, this latency for this time, and then something else for the next 5 minutes. And what is the price for that? And the provider sends out the pricing information, and they try to find a matching.
Yeah, got it. Very cool. Thank you.
Hi, Devnil from VMware. I guess I'm kind of curious about the user side interaction with the blockchain. So, how does the user top up their wallet? How do they do things like key management? I guess, what does the user interaction with the blockchain look like? Because that might just be an obstacle for a lot of people who don't know much about how to do that.
Okay, so the immediate response to that would be you would just have some sort of an application on the user equipment, maybe on your phone or your computer, and with that, very similar to how you manage your keys for other crypto exchanges or some other wallets. But if you want to discuss more about this, I would like to encourage you to come and talk to us afterwards, and probably Ranveer will have detailed answers about how we're implementing it for our case.
Cool, that's good.
Hi, Tal from UT Austin here. So I'm wondering what necessitates the use of blockchain here. Is it trust? Is the trust between the user and the service provider, or is the service provider so bad that they need some kind of distributed ledger to make sure things are not altered?
Yes, great question. So when there is payments involved, we need to make sure that the same money is not spent twice, right? Now, that means when I'm sending some payments to a service provider, it needs to be recorded somewhere. So technically, a credit card company could do that as well. But the dynamical nature of this cellular environment we're talking, payments going every couple of seconds and contracts being made maybe every couple of hours or days, we are trying to build an environment that can cope up with this dynamicity and also provide this trust-free nature so that we don't need to rely on any centralized third parties. And we believe this would also reduce the prices as well.
I see. Thank you.
So I have one question. Do you see scenarios where existing carriers, operators would want to use the system as well?
Yes, actually, this is how we would start deploying this approach. So, as I said, there is no single operator in US that can provide 5G everywhere. So, if I were AT&T, I would try to encourage my users to start a similar service when I don't have base stations in that area, but Verizon has, so that they can connect to Verizon. And in the opposite case, Verizon subscribers, when there is no Verizon base stations around, can use my network by using this system here.
It's a cool peering kind of an agreement. So let's thank Serhat again. And I would like to invite all speakers, Kunbu, Haofan, Dong, over here as well for the panel. Serhat, you can sit here as well. Yeah, Parijiko.
Yeah, thank you so much. Serhat, I'm curious to hear a little bit more about about your initial directions for privacy. So it seems like the information that you're posting to the blockchain is probably going to be fairly sensitive, if I understand what's going on with these two-sided measurements. A lot of general purpose tools for providing privacy on blockchains involve expensive zero-knowledge proofs, which provide a really intense overhead for provers. It seems unlikely that you could generate these proofs efficiently on mobile devices. So I'm curious about your initial directions for privacy here.
Correct. So obviously there's a lot more work to be done in this area, but our initial perspective on this is that on the blockchain, the provider is only signing this supplier contract that I mentioned, which talks about the service details. And the consumer only signs some consumer contract that declares an escrow amount. And the micropayments do not touch the blockchain. So on the blockchain, you cannot actually track when did the user actually send those micropayments and for which service they send it for. You can only track the total amount of payments after some long time interval paid to the bridge. And we don't even know which service provider it was for. So this is like the initial layer of privacy we can come up with. But yeah, thank you so much.
Hari Balakrishnan. So on the last talk, I don't understand one key thing. So on the internet today, when I buy internet service, there's some contract. Most of us don't read it. And probably this says something about performance. And if it doesn't work for some period of time, I might change providers, I might complain on social media, I might be able to take them to some legal situation, right? Legal proceedings. Then you look at helium, it doesn't really make any guarantees on performance, as I understand the helium network. It uses blockchain. In your proposal, the thing I don't get is, I understand I think I understand the two-sided measurement path, but let's suppose I connect to one of these small micro ISPs with whom I don't even have any legal contract. I send some data or want to receive, I send some data. How do you protect against, you actually deliver, the ISP, micro ISP delivers the data or sends it on, but I then say, you know what, it never came. Or conversely, I send it and what proof do I have? Like, okay, I suppose I didn't get it, but all the measurements in the places where you measure work. What actually ties it together so there's actually proof that the network did its job?
Great question. So the reason why we have micropayments and incremental SLAs is that we can decide on the performance of the provider in a real quick fashion. Let's say in a couple of seconds, maybe 10 seconds. Every 10 seconds we measure and let's say I'm the user. I can measure for the next 10 seconds about the throughput that I'm achieving with my end-to-end application.
Yeah.
And if the throughput is good enough for me, yes, I send the payment. If not, I stop the payment, claiming that I was not receiving the service I was promised for. And with that, the provider will obviously not receive the payment and stop providing service. So we will be done.
I see. So every few megabytes or whatever, I have to keep issuing this. So if everybody does this, and every one of these generates a transaction on the blockchain?
No, that's the great
Or
thing.
it's aggregated or something?
Yes, so we are creating payment channels on the blockchain. These are what the consumer and the supplier contracts are for.
Yeah.
And under those contracts, actually, we can send micropayments only to the bridge without touching the blockchain. And the bridge will just forward those payments. And when we are done with settling with our contracts, we will just settle with the bridge. And that's the time when we touch the blockchain.
So the difference between this and helium, this proposal and helium, is that these contracts are short-term performance contracts.
Actually, not quite. So the contracts we sign, let's say I'm the user again, I'm signing the consumer contract. At the time that I'm signing the consumer contract, I actually don't declare any intent about performance. And the bridge does not promise anything because it doesn't really know. When I want to connect to a particular mini telco, that's the time I talk to bridge and, okay, what is available in that mini telco? And then I start sending payments according to the service that I expect to receive. But again, the blockchain does not know anything about the performance details. As long as I send enough money to the bridge, which gets forwarded to the mini telco, the mini telco continues providing the service to me. And if I am not satisfied with it, I just don't send, and the relationship between me and the mini telco is completely removed.
So the money is by the amount of data delivered or the rate of data delivered?
That's the different kinds of SLAs you can sign up with. So you can sign up for some usage SLAs where you pay by the amount of data that you send, or you can pay by the throughput, or we can come up with different kinds of two-sided measurements, such as latency is the one that I'm currently working on. Maybe you can come up with some loss-based SLAs.
Thanks. Hi, I'm Madhav from UT Austin. So my question is on Wi-Fi localization. So with the question of privacy and tracking, we see probing being turned off completely, or even if it's not turned off completely, we see MAC address randomization, and the probing itself is pretty inconsistent, like depends on whether the device is actively turned on looking for networks. So do you see this as damaging for any of your use cases? Because even if you are able to identify the location, you don't know the actual device, so you are not able to, like, especially the use cases you discussed.
Yeah, thank you for the good question. So we for the MAC address randomization, we actually discussed this in the paper. As you mentioned, if we don't know what the target device address, it's meaningless to basically localize it. So our solution is like we noticed that the target the device the target device that send fixed random MAC address to each access point. That this binding is between the access point name, basically the Wi-Fi network name, with the device. So if the device wants to associate with, for example, UT Austin Wi-Fi, and it always probe with a fixed MAC address, even it's random, it's a fixed MAC address to that Wi-Fi. So what we can do is like we generate fake beacons and broadcast it to trick on each channel to trick that the device, the target device, that we have UT Austin Wi-Fi, for example, on each channels. And in that case, we can get consistent MAC address. So, and in that way, we identify the target device. So you can refer to our paper if I not explain it very clearly.
Yeah. And another question would be that most of the low power IoT devices, they are only accustomed with 2.4 gigahertz antennas. So that you would be limited by just 11 choices of 11 channels, right? 11 frequencies.
Mhm.
So you would be limited by 11 points in the 360 degree for your localization. So how would you plan to increase the resolution here?
You mean the direction finding
The direction,
resolution,
yeah,
right?
because you only have 11 frequencies to probe on.
Yeah, that's a good question. And our solution to that, we also mentioned this in paper. So we do interpolation between these points. And for example, the target device is between channel 10 and 11. And there's a trend between like 10 is higher and the 11 is a little bit lower, but there's a peak here. And we can find the peak based on interpolation to find a more accurate direction. Yeah. Thank you for the good question.
Hello, I'm Was from UT Austin. Yeah, I have a question for the acoustic sensing. So what's the sensing range like of your system? Because with acoustic sensing, I believe I haven't worked like with an acoustic system right now, but I think that their sensing range is very limited. And so given that range, what sort of applications you're envisioning that like your fine-grained sensing, what sort of applications can like benefit from that thing? And there's a graph like in your paper, like graph 9A. And in that graph, like they were like testing the impact of distance, on like measuring the vibration amplitude. So in the like when the device is closer to the like if the phone is closer to the vibrations device, so the higher order, like the original intermediate frequency, if you measure like amplitude from that, the error is higher as compared to the third order intermediate frequency. And as the distance grows, the intermediate frequency error like goes down. So why is that? I was like confused, like because third order harmonic should have like less contribution than the first order harmonic, given the closer distance.
Okay, thanks you for the great question. So with respect to the first one, so the sensing range for our current system is like around 15 to 20 centimeter. The reason, yeah, as you mentioned, the sensing range for acoustic sensing is very limited because of the fast attenuation over distance, and also like since we are using the nonlinear signals to boost the sensing granularity, the sensing range is even shorter than the private studies. The application we are targeting at is that, for example, the machine vibration, we can detect the vibration of the machines to diagnose if there is any problem for the machine. Yeah. And for the second problem, can you repeat again?
Yeah, so the question was like related to the graph and your papers. Like the topic was like impact of distance. Like if you move a phone away from the vibration device. So in the graph, like if the phone is closer to the vibration device, if you measure the vibration amplitude given using the first order intermediate frequency, the error is higher as compared to the third order, like given the distance is 0.15 meters, like 15 centimeters. But as the distance grows, this flips, like the error with intermediate frequency, like first order harmonic, it decreases, and the third order it increases. But I think is it due to a multipath effect, or like what's the?
Oh, I got a good catch. Actually, the reason why when the device is close to the target, I mean, the higher order is more accurate, is that as I show in the slides, the higher order usually, if we have enough SNR for the higher order intermodulated signal, with the same displacement, the phase variations for higher order intermodulated signal is much larger. So if we have much larger phase variations, then we can have more accurate, displacement estimation, right? However, if the distance increases, the strength of the higher order intermodulated signal becomes weaker. That's why, like the third order intermodulated signal becomes much better when the distance increases.
Makes sense. Thank
Good
you.
catch. Thank you.
Yeah, this is very short question for Wordy. I think this is quite great approach because soft handover is crucial in satellite communication because we can only see the several minutes in visible satellites in specific region. So by the way, I'm curious about the penalty or delay that can happen during the soft handover because I think I'm researching on the handover decision in satellite communication. But so in your Wally mechanism, is there any penalty or delay when we are doing soft hander from changing some one satellite in that combination?
Thank you for the question. And first thing that I can think of is that compared to the regular antenna patch, number of configuration that you need to set for the Wally, because this is meta-aram, there are much more. So in terms of that takes a delay because there are much more configuration to find and fix. And also, in order to do a fast handover, you need to do a beam alignment establishment, right? Actually, there is you can create multiple beam out of Wally. So one good thing is that you can use a multiple beam to do a beam search. So I would say rather than a penalty, that's an advantage that you can shape multiple beam to do a fast beam search on the secondary satellite. But with that also, you need to do a lot of search on finding phase and what kind of array factor you need to make. So I guess there's trade-offs.
Thank you. Well, thank you. Let's thank the speakers again.